Okay, so for the next few slides, use the notes that I gave you just to recall properties about logarithmic functions. So chapter 5, this is our last chapter to develop truly the rest of our derivative and integral tools. Okay, the natural log of e is 1. Why is that? Base of the logarithm, or the natural log is e, so e to the first power is e. ln of 1 is 0. When you're multiplying functions, you can split them up by adding the natural log of both functions. When you're dividing functions, you can split them up by subtracting natural log of the numerator minus natural log of the denominator. And natural log is useful for solving exponential functions because it enables us to bring the exponent to the front of the logarithmic function. These will aid us in simplifying derivative problems, so we will come back to these. Alright, the natural log function is defined as an integral. So the natural log is the definite integral from 1 to x of 1 over t. So let's think about what our inverse graph looks like. This is the graph of 1 over x, but we look specifically in the first quadrant. Okay, so x has to be a positive number. If x is bigger than 1, so if our boundary is bigger than 1, well then what do we know about the value of the integral? It'll be positive. So what does that mean in terms of the natural log? The natural log is positive for any value of x bigger than 1. If x is less than 1, then think about your definite integral. If I plug in a number less than 1 for x, I have to use my property of switching the boundaries. So these values will all be negative. Okay, so we would be looking, this is where x would be less than 1. But by the initial property, it has to be bigger than 0. So if we were using our calculator, the natural log will be a negative number for any value of x between 0 and 1. Okay, so this is the graph of the natural log of x. Okay, so again, natural log of x is defined as the area under the curve 1 over t from 1 to x, and x has to be a positive number. So that's our domain. Soft bracket 0 to infinity. Okay, natural log of 0 does not exist. Our range, our y values can be any real number. Okay, notice our function is continuous on the domain. The function is increasing. Okay, so let's think, what does that mean in terms of the derivative? That means the derivative will always be positive, and our function is strictly concave down. So let's talk about what that means in terms of the first and second derivative. So that means the first derivative is decreasing. Okay, let's think about if we look at tangent lines, slope of tangent lines. The slope here starts out as a positive value, and as x increases, the slope approaches 0. So the slope decreases, and that means that the second derivative will be strictly negative. Okay, so the derivative of the natural log function. If this is how the natural log function is defined, then what if we took the derivative of both sides of this equation? So by our second fundamental theorem, when we take the derivative of this, we replace t with the variable x, and this is the derivative. Now that's very limited. So in addition to all your derivative rules, power, product, quotient, chain, implicit, trig, now we have a new derivative rule. When we derive the natural log of an expression, 1 over that expression, and then we need to multiply by the derivative of whatever the expression is. Okay, so 1 over x is a very limited view because we know that we have more things happening to the function than just a single x. The derivative of the natural log of the absolute value of u is the exact same. Okay, so times u prime. So you'll see me write them both ways. The importance of the absolute value comes next lesson when we integrate the function. So natural log of u, natural log of the absolute value of u, they have the same derivatives. Okay. So find the derivative of each. And again, natural log is just a new rule. We can combine it with any other derivative rule we've learned. So f of x equals the natural log of x minus 1. So the derivative, 1 over x minus 1 times the derivative of the expression, which is just 1. H of x is the natural log of 2x squared plus 1. So the derivative, work from the outside in, it would be like the process we talked about with the chain rule. 1 over the expression times the derivative of the expression. So we can write that as a single fraction. Let me see. Oh yeah. Oops, sorry, I did include g. Alright. Y equals x squared ln of x. So now we'll need our product rule because we're multiplying two functions in terms of x. First times the derivative of the second plus the second function times the derivative of the first function. So cleaning up our answer, x squared divided by x would simplify to x. Remember, ln is a function. Treat it like the sine or cosine, which means I cannot multiply those two things together. So we'll write it as plus 2x ln of x so that that doesn't get confused. Ln square root of x squared minus 4. So look at x, it's being squared. You're taking the square root of that whole expression, and then you're taking the natural log of it. So when we think about our chain rule, working from the outside in, the first function we would derive is the natural log. So 1 over, keep the expression exactly the same. Now multiply by the derivative of the square root. Bring the exponent down, subtract 1 from the exponent. And with the chain rule, you have to keep that inside function exactly the same. And then lastly, multiply by the derivative of the inside. So the derivative of x squared minus 4 would give us 2x. So it would need to be simplified. Right? We have a negative exponent. We'll have to make that positive. The 2's will cancel. So we have x over the square root of x squared minus 4 times the square root of x squared minus 4. We can simplify this. So that's what I would expect to see for the final answer. Alright, let's look at use some properties of the natural log. Okay, so from the first slide we said the natural log of a divided by b could be split up as the natural log of a times the natural log of b. So we're going to do that here before we attempt the derivative, because if we didn't, think about what the derivative of the natural log is. It's 1 over this expression, and then you have to derive this expression, which would use the quotient rule. So let's use the property, and we'll rewrite this as the natural log of 2x minus the natural log of x plus 3. Okay, so no derivative yet. Now when we go to determine the derivative, we can just apply the individual rule to each term. So derivative of ln of 2x, 1 over 2x times 2. and I'm going to subtract the derivative of the natural log of x over x plus 3. So it would simplify to 1 over x minus 1 over x plus 3. Now I'm happy here with your answer, and we talk about this. If you were to check on CalcChat, they would get a common denominator, but it's not necessary for what I want you to do. So the CalcChat answer, x plus 3, would look like this. Multiple choice purposes, checking your answers, just know that these two things are equivalent. Both are acceptable. Alright. ln of t divided by t. Now for this problem, that rule we just used doesn't apply because it's not the natural log of the expression being divided. The natural log is only in the numerator. So for this problem, we would have to use the quotient rule. So bottom function times the derivative of the top function minus top times the derivative of the bottom all over bottom squared. So it's a nice, easy simplification. All done. ln absolute value of cosecant of x equals y. So here we are, exact same derivative rule. 1 over the expression times the derivative of cosecant, negative cosecant x, cotangent x. These would cancel. Y prime, sorry. So the derivative would be negative cotangent of x. Alright, y equals natural log of the natural log of x. Chain rule, working from the outside in. First derive this natural log function. So it's 1 over whatever follows it. Multiply by the derivative of the expression. Derivative of ln of x is 1 over x. Again, these things cannot be multiplied. So we would write it as x ln of x. Okay, if g of x is defined as the integral from 1 to ln of x of t squared plus 3 dt, and I want to find the derivative of g prime. So using the second fundamental theorem, replace t with the function in terms of x, and then multiply by the derivative of the boundary. Now be careful, this whole expression, if we wanted to write it as one fraction, ln of x quantity squared plus 3, all divided by x. Let's see. Oh, cut off a little bit. Find the equation of the line tangent to this function at the given point. Equation of a tangent line, back to point slope form. Okay, so certainly not nice looking, but we have our coordinates of the point of tangency. Now we need our slope, and we know the slope comes from the derivative of the function. Alright, so deriving this, working from the outside in, 1 over the entire expression, that's the derivative of the natural log. Now derive the square root, so 1/2 times the expression to the negative 1/2 power. The expression stays exactly the same. Now multiply by the derivative of the inside. The derivative of the inside is the chain rule again. Outermost function is the squaring function. So 2 times that function to the first power. And what were we squaring? We were squaring the sine of x. And then lastly, multiplied by the derivative of sine, which is positive cosine. Okay, so for homework, I want you to simplify this derivative and find the slope. So determine what f prime of pi over 4 is. Okay?